Hello, I'm Lindell Ormsbee, and I'm with the EWRI Water Distribution Systems Analysis Committee, and I'm with the task force task committee that's looking at the history of water distribution systems analysis. And as part of our task committee, we have been interviewing various pioneers in the field of water resources distribution analysis and getting insights from their past and some of the work that they've done. And today we're interviewing Dr. Srini Lingireddy and talking with him. And this interview is being conducted on May 23rd in Sacramento, California, 2017. And so, Srini, I just wanted to start out the interview asking you how you really kind of got interested in water distribution analysis and how you found your way to the States and starting to partner with Dr. Don Wood.
Thank you, Lindell. Thanks for taking time to talk to me about this. I know I joined the University of Kentucky in 1991. Prior to that, I was at Indian Institute of Technology working on water distribution system analysis.
Okay.
Basically looking at how to model the intermittent water systems.
Okay,
intermittent water. Doing the pressure dependent flow analysis.
Okay.
And I contacted Don, whether I can come and work with him.
Right.
And you also responded yes.
Right.
And that's how I came to University of Kentucky.
Okay. Well, were you working with anyone in India at the time before you came over? Any professors there that?
Yeah, Professor K. Ilango.
Okay.
He was my PhD advisor.
Okay.
And that's how I got into this. I must really thank him for getting me into this. I was not interested in this area. I wanted to go into groundwater, but somehow he convinced me to get into water distribution.
Okay. Well, we're fortunate that he did. So when you came over and started working with Don, what was some of the initial things you started looking at or were focusing on?
Two things. One was NSF funded project, which you were the PI.
Right.
And the optimization, things like that.
Okay.
And that's the second one was with Don Wood. Forgot the nuclear power station.
Okay.
We were making the changes to the code to look at the minor loss coefficients. The T and Y junctions.
Right.
And that's the Savannah River project.
So why was that important for because most models don't, they just use K coefficients or something. So why was it important to have a better characterization of the minor losses for the? Minor
losses are generally, we say minor losses because they are so little compared to the frictional losses in the pipeline in most of the water distribution systems.
Right.
When we are working with pipelines, numerous pipelines that are short length pipelines with the numerous intersections,
right.
The so-called minor losses, they dominate the friction.
Okay.
And if we do not quantify them properly, your resulting flow rate and pressure results are going to be significantly off. And the K values that we use, like 0.3, 1.3, like that, at T and Y junctions, they're not enough. And the actual the losses depend significantly on the flow rate, the ratio of the flow rate incoming, outgoing, and the area characteristics. Quite complex relationships.
Okay, yeah. So that was important for the nuclear power
plants. Nuclear power plants, okay. Yeah. And it's also true with any water distribution system that has short length pipelines.
Okay.
Things like a distribution system within a process plant, like a water treatment plant, where we are moving water from one process to another process, in short length pipelines.
Okay. Now, in the nuclear plants, are they still typically turbulent flow, or are they laminar flows?
They are turbulent flow, very high velocities.
Okay.
Very high velocities.
All right. Well, what are a few other things you remember about your time at UK? I guess you were there from 91 to, what was it?
2007.
Okay. So can you remember any interesting things that happened while you were there, or that?
Other than having
you
my finger.
cut your finger off in the lab, right?
Yeah. Yes.
How did that happen?
Yeah, we were doing some experiments on the open channel flume.
Right.
And I was trying to lift the flume up and set up, the slope.
Right.
Designated value. was not moving. The gearbox was not moving, so I went there to try to fix that, and that's when I realized the finger was gone.
Okay.
Yeah.
Well, so you literally took things in your own hands there, right? So.
Yes, we used to do a lot of work in the lab.
Right.
And in continuation to that, minor loss coefficients at T and Y junctions, we did a lot of experimental work too.
Okay.
To corroborate the equations.
Okay.
So that's how I was involved with the lab.
All right. As I recall, you had an interesting run-in with a manometer or something too, didn't you?
God. Yeah, I did. A mercury manometer, the connecting tube snapped off.
Yeah.
Spilled the mercury into the open, the flume. And as my duty, I reported that diligently. And then later on, we found that there were many such incidents.
Right.
And we found in the past, and we found a bunch of in the mercury in there.
Yeah. Okay. So they came in. I remember with hazmat suits and stuff. It was quite a.
That's true.
Quite a fiasco.
That's true, but I don't know if I did the right thing.
Yes, you did. You did.
Yes.
So, but we're glad you're still here with us.
Yeah.
So when did you decide to leave UK and go back to India and start a firm?
2005, I was up for sabbatical, and then I thought, okay, I'll take that opportunity, just go travel the world and see what's going on in other parts of the world.
Right.
And at that time, I was very closely involved with the KY Pipe program.
Right.
And I was doing training, I was doing, development. And I thought, okay, it's a good opportunity to go explore the world. And I went to Israel to give a training on transients and met a guy from India. He said, I told him I'm exploring for opportunities. He said, leave it to me. There is so much work in India. And, you do the technical stuff, I'll do the rest of the things. Let's try.
Okay.
So when I was there, I was, in India, I explored this and then actually, did a bunch of work in Oman, Middle East.
Okay.
During that period. And then I came back and stayed at UK for 1 year. And during that time also, there were a lot of opportunities coming at my, door.
Right.
I could not refuse.
Okay.
So I decided to leave in 2007.
Okay, so you went back to India, and did you start like a firm, or what happened?
I worked with another firm that was already set up.
Okay.
They were into water control systems.
Okay.
Not distribution modeling, anything like that. Flow control valves, pressure reducing valves.
Right.
They're the distributors. And when I got into this, I introduced new technologies like bladder vessels.
Okay.
And how to protect the systems more economical ways and more efficient ways. So that's how I got started.
Okay. So what were some of the insights that you were able to I guess add to the business?
It's all the training that I received at Kentucky.
Okay.
Both training and experience. Looking at both water distribution, like I said, as part of Kentucky, the KY Pipe program, I was in contact with practitioners.
Right.
We used to do a lot of training together. You were involved with that too. Mm-hmm. So that's how, I got to know a lot about practice.
Okay.
And when, just to go back, when I was doing PhD, I was at Indian Institute of Technology for about 6-7 years, master's and PhD. I was very closely involved with the campus. We had 640 acres campus, self-sufficient. It's like a mini township. And my professor was the chairman of the estate committee, and we used to basically run the entire operation there, sit there and then. So I was involved with the water supply systems. We were calibrating water meters.
Okay.
As part of that. So I had a lot of exposure. I mean, I wouldn't say it's a tremendous experience, but
you had some
practical experience with the water distribution systems and the limitations and things like that.
Okay.
So that's how I got into this, and I thought I could make some difference.
So how did that help your research? Just having some of that practical experience and
working
facing with consultants and
a lot. For example, the calibration. somebody approached us, to do the calibration. At that time, we were doing some manual calibration, and we said, okay, we could, set up an optimization routine for that.
Right.
So things like that, and then I got shifted slowly into transients.
Right.
My first transient modeling experience was, I think, back in '92.
Okay.
So that's how I got very closely involved with Dr. Funk.
Right,
Jim Funk.
Yeah.
And Dr. Wood. These they were the pioneers in this area.
Right.
So I was helping them with modeling.
Okay.
And learn the trade.
Okay.
Yeah.
Yeah, as I recall, you developed a calibration code using a GA approach, and that was back in the 90s. That was pretty early, wasn't it?
Right, and I was actually looking at, my PhD thesis partly was on pressure-dependent flow analysis, the hydraulic analysis part of it.
Right.
And then an optimization on top of it. I was tinkering with genetic algorithm code at that time, but then the tools were not available. The tools we had were too slow. We could not do that.
Right.
But then in about 92, 93, 94, when I come to UK, there were enough tools for me to explore this possibility.
Okay.
And that's how we have come up with. And you are very much part of that. And it's all your guidance. How we did that.
Okay.
Yeah.
So you got involved in transient analysis, and I think that's kind of become more of your focus.
Yes.
At this time. Is
Yes.
that right?
Yes. And again, the reason for that was there was a lot of shift at that point in time, about mid 90s, the late 90s. About pathogen intrusion, the scare about pathogen intrusion in distribution systems.
Okay.
And we were part of AWRF and EPA funded study, and that's how I got more closely involved. We developed we modified the code to do those pathogen intrusion calculations.
Right.
And then we started adding a lot more features to the software at that time.
Okay. Okay. As I recall, part of the transient work, you also were involved in training as well, and
Yes.
now that you've gone to India, I guess that's kind of become more of your focus is transient work.
Transients mainly because in transients, again, while at university, I was also in contact with many manufacturers of surge protection equipment. And everybody had their own thinking. My product is the only one, that will protect the pipeline system.
Right.
And with my optimization background, all the training that I had at Kentucky, I said, no, each system is different. It can be protected many different ways. So if you can combine the techniques, combine, the different tools, you can come up with a more optimal economical protection system, more efficient protection system. And that's how I got started.
Now, when you all do transient analysis, I think some of the early methodologies use the method of characteristics.
Right.
And I think Donna developed a
wave plan method.
A wave plan method. Can you briefly describe kind of just quickly the distinctions between those two?
Well, they both start with exactly the same identical equations,
Right.
Both momentum and continuity equations. And, the approach is different. It's like Lagrangian versus Eulerian approach.
Okay.
Okay, that's the only difference. Either you divide the your field into time, the space, the configuration, or you just follow the waves, and keep track of the waves. And the wave plan method does this. The other method does the space time, discretization. Other than that, absolutely no difference. And because the wave plan method just follows this, and the water distribution systems, they're not like groundwater models, the complete discretization. So if you just follow the wave along the pipeline, it's going to reduce the overall cost of computation significantly. You don't need to do the calculations where you don't have to.
Okay.
And that's how this is much faster, and that's what is allowing us to do a very large distribution systems, surge analysis for that very quickly.
So what are some of the distinctions between a lot of the systems in India than the U.S.? I know we've talked about in the past some of the differences.
In terms of distribution side, once you have the water, distribute to the consumer side. The main difference is intermittent nature. Okay, here water supply is continuous. Most of the developing world, water distribution is intermittent. India has no exception. India, the last at least a decade, they have been investing a lot of money trying to move into continuous water supply, and so far there have been claims that success stories are there, but I tend to dispute, and not a single utility can claim with 100% certainty that they are supplying water 24/7. And there are a lot of structural problems and also sociological problems.
Right.
Okay, and so it's basically you have resources. 20-30 years ago, source was a problem. Now source is not a problem. Resources are not a problem in terms of money. It's the approach. And just give one example, elevated storage tanks. We have a lot of elevated storage just like here, but they are different. Here, elevated storage tank is a floating tank. There is only one pipe connecting the volume to the bottom of the pipeline.
Okay.
When there is a high pressure in the pipeline, water goes into the tank, otherwise water goes out of the tank. All tanks in India, like one-way tanks. Water enters at the top, leaves at the bottom.
Okay.
Okay, and there is that means essentially whatever distribution system is there attached to that tank is independent.
Okay.
So it's independent. From that point of view, it's even easier to control, but there are other problems why we are not able to control. Every household has indoor plumbing, but there is something in between. There is a storage that comes between the distribution network and the indoor plumbing, either at the ground level or at the overhead tank.
Okay.
Okay, unless you get rid of that, you're not going to have, what people do, they estimate the demands, the consumption, what is required, and put a diurnal demand curve for 24 hours operation.
Right.
And design the system, say that, okay, if the residual pressure is greater than the required value, my design is satisfactory. But then the water is not going directly into the plumbing, indoor plumbing, it's going into an underground sump. The residual head is 0, not 12 meters to 13 meters.
Right.
It drains very quickly. And metering is not there. Even if you have a meter, the meter that's designed for certain flow rates, now it's spinning at 4 or 5 times. That gets damaged very quickly, and nobody wants to pay for that kind of thing. So these are all the simple things. If we can get rid of this intermittent storage, you can go to 24/7. But people don't want to get rid of the intermittent storage because we are not assuring the bulk water supply. There are all minor issues, primarily the surge related issues on the the bulk water supply side.
Uh-huh.
Okay, so once we fix the problem on the bulk water supply side, increase the reliability, tremendous improvement.
Okay. Okay. So what advice would you give based on your career? What advice would you give to some new researchers that are kind of joining the field? Any insights that you might give? Of course, you were in academia for a while and then made the decision to go into private practice. Just some general advice that you have for some of the people who might be watching the video.
Over 75% of the population are going through intermittent water supply. They don't have the water, they don't receive water on a daily basis.
Okay.
Even if they get water on a daily basis, it's 1 or 2 hours a day, and that means the rest of the time the pipeline is drained. And doesn't matter which part of the world you go, there are leakages, the joints leak. And when you have water in the pipeline, that's no problem. It's water is going out. You're still losing water, but that's not a big issue. When the same joints, when you drain the pipeline, dirty water is coming back into the pipeline. Okay, so and this intermittent nature is making the pipeline deteriorate very rapidly. You have expansion and contraction happening day in and day out. Air release, is the worst thing. I mean, the air management is really, that's something that I've learned over a long period of time, my specialty too. So if we, there is a lot of interest in that area. Not so much, network modeling now I think we have addressed enough. You can always, there is an incremental change in terms of how to speed up the process, so you can embed that into optimization tools and things like that. But there are a lot of other practical the difficulties. How do you model these pressure dependent flow calculations? unless you understand that part, how do you fix the problems in there?
So what you're saying is there's a lot of other problems out there.
Practical problems.
Practical problems
Yes.
that you suggest maybe people start looking at some of those.
Exactly. And as part of ASEWRI, we have an intermittent water supply task committee. We're trying to draft, the various problems associated with that, and if somebody can contribute, that would be wonderful.
Okay. Well, any final lessons learned that you've gleaned over years? Any couple of bits of wisdom you could impart?
Don't trust model results at the face value.
Okay.
Okay, and develop tools to process the results. We still don't have good tools to process the results. Okay, so process the results in a way like what we're looking at big data. It is like big data in a different way. So we need to have tools that are that are going to extract the information from these results and then throw at your face. Okay, a warning signs and things like that. So it is difficult task. When you're working with a large distribution system, one small error somewhere, especially on the transient side, can destroy the whole thing. Can change the whole thing. So always, that's what I'm trying to do. As sometimes as part of the KY pipe, the software, or for my own internal use, I have so many checks and balances. Every time a surge analysis is done, it goes through this quality check because I'm worried. One small mistake that I make can really have a devastating effect on the surge systems.
Right.
So that's all. Don't trust the results blindly, and then
double check. Think about what you're doing.
Double check the data, boundary conditions, and things like. And more importantly, when you're doing the modeling, especially on the transient side, understand how the equipment that we're going to use as part of protection is that translated right into your model.
Okay.
A lot more complex than a steady state. The pump is a pump. You have a characteristic curve. A small variation here and there is not going to make a big difference.
Right.
Whereas these control valves, surge protection equipment, if an air valve is not just an air valve. A 2-inch air valve or a 4-inch air valve from different manufacturers have different characteristics. So be extremely careful in translating that data and viewing the results.
Okay. Thanks so much, Srini. It's been great to
Thank you very much. I'd like to thank EWRI and Dr. Grayman as well. Thank you.